the most ubiquitous equation in all pop science. Energy is mass, and mass is energy. Nuclear bombs, stars, fusion. Conceptually, it doesn't quite make sense how something ethereal like electricity or heat can be the same as something tangible like a dumbbell or a crunch wrap. But give me a shot to change that. If you've ever tried researching how mass and energy are one and the same, you've probably come across statements like, only 1% of your mass is the actual mass of the particles. The rest is the binding and kinetic energy of those particles. Or, the Higgs mechanism is only responsible for this 1% of mass. Now this is confusing. How is kinetic energy mass? What is the Higgs mechanism? And what does that mean to give mass? It's such a conceptually confusing idea. Well, let's start over. We start with the broad picture. Particles. Particles are excitations in quantum fields. The intensity of excitation is what we refer to as energy. Since particles are also waves, when they are moving around, they possess more energy. If we want to compare two particles, it doesn't make sense to compare their energy if they are moving around. So we either stop them or catch up and enter the same frame of reference so they appear motionless. Now we can see how much energy they have. In fact, that's what the masses of particles are. The up quark has a mass of 2 mega electron volts, which is 3.2 times 10 to the minus 13th joules. It's energy. For particles, mass is the amount of energy that particle possesses at rest or in the same frame of reference as the observer. Or, mass is motionless energy. When we move to a bigger scale from particles, we have to slightly modify that phrase and definition. Otherwise, it doesn't make sense how kinetic energy can contribute to mass when we say mass is the energy of particles at rest. For larger realms, we say mass is energy confined to an arbitrary system. What does that mean? Let's imagine a simple proton. Conceptually, we see a particle, a sphere, and so of course it has mass. Particles or spheres have mass. Now we look inside the proton and we see 3 more particles or quarks. This is a little uncomfortable. I like mass to have boundaries. But I see 3 new particles, and of course particles or spheres have mass, so it makes sense that the proton that they make up has mass. We then take out these 3 new particles and put them on a scale opposite another proton. Now we see the proton weighs almost 100 times more than these 3 particles. I don't like that. That's not the mass I know. When we look back at the quarks in a proton, suddenly now they are waves. This is even more uncomfortable. But the longer I look, I see they more or less still fit in this imaginary boundary we've defined as a proton, so I guess yeah, it's easy to imagine they still have mass. But why does this weigh less than a proton? What we are missing is the other energy not on display here. The quarks in the proton are held together by the gluon field, or rather they create a gluon vacuum or flux tube in between them that sucks them together. Now we say vacuum, but really it's just an absence of gluon field fluctuations. The universe wants there to be quantum fluctuations here, so this vacuum is preventing that from happening, which is energy. It takes energy to stop quantum fluctuations. Ergo, this vacuum represents a localization of energy in the gluon field. I'll connect the quarks with little springies so it's more evident there's gluon energy here. Now, the internal composition of protons is still contested. Evidence suggests there could be a 4th quark, and multiple quarks do continuously form and disappear. One interpretation of a proton looks like this. But that's not the point. The point is, all of these constituents, quarks, gluons, and the kinetic energy from their motion are stable and trapped in this volume. They won't leave or intrinsically power any other process. Mass is energy confined to an arbitrary system. Nothing here is conceptually anything but waves or excitations of energy. The only difference is that their presence and interactions keep them contained in this little volume, unable to leave and do anything else. I can now define our arbitrary system as this volume, and suddenly it's motionless. Now I just measure how much energy is here, which appears to be 938 mega electron volts. I can now say the mass of a proton is 938 mega electron volts. If we think of a photon or light, this is pure energy. It has no mass because it is never motionless. But if we had two imaginary boxes that were white bodies, theoretical matter that would absorb zero light, and we trapped a photon inside one and closed it, then that photon would bounce around forever on the inside. If we were to somehow measure the masses of these two boxes with the precision of a photon, we'd find that the box with the photon had greater mass. Now you may be thinking, well, that kind of doesn't make sense. And you're not wrong. It's not intuitive. How can a photon bouncing around inside add mass or cause the box to weigh more? Well, that's that darn Einstein again. You see, although light doesn't have mass, it has momentum. Ooh, didn't see you there. So if it smacks into something, it will exert a tiny amount of radiative impulse. This impulse increases the shinier or more reflective a surface is. This is how solar sails work. When we weigh this box, or anything else, we are measuring how strongly it interacts with a gravitational field. The bottom of the box is further down the gravity well, or closer to the source of gravity than the top. You may not know this, but gravity gets stronger the closer you get to the source. And you also might not know this, but light becomes more energetic as it moves down a gravity well, or its momentum increases. Now we are talking absolutely infinitesimally small amounts that no real experiment would ever be able to detect. But, believe it or not, the photon hits the bottom of the box with slightly more momentum than when it hits the top of the box. So if you were to add those forces together, you'd see, by golly, the box is experiencing a tiny, tiny, tiny downward force from the photon. In fact, the trapped photons in the sun contribute to its mass. But this is an incredibly tiny amount. If we assume photons take on average 500,000 years to escape the sun, then they contribute only about 1% the mass of the Earth, or 34 billionths the mass of the sun, to the overall mass. You may be thinking, oh yes, of course, mass is energy confined to a system or volume. I get it now. But let me ask you, an electron and a photon are both fundamental particles, yet the electron has mass, but the photon does not. Why is that? This confusion arises because the idea of what is mass is incomplete without the discussion of inertia. Inertia is an intrinsic property of mass, and it describes a mass's unwillingness to change frames of reference. Or, in simple terms, it's difficult to accelerate masses. Why is that? Earlier, we saw that the quarks inside our proton are actually complex wave functions. Waves and wave functions, however, are very dependent on the frame of reference in which they are observed. If we look at these two waves, the top one clearly has a higher frequency than the bottom one. Therefore, the top wave has more energy. But if I zoom out, we see they are the exact same wave. I'm just moving the top one to the left. If we return to our proton, this little volume of energy is stable in this frame of reference. As soon as I try to move it, I start changing the wave functions of all of its constituents. That flux tube in the gluon field stretches and compresses, which increases or decreases the resistance between the connecting quarks. The wave function of the quarks themselves now appear to vibrate faster and interact more with the Higgs field relative to the old frame of reference. These faster vibrating wave functions have more energy than before. It takes energy to change this energy. That is inertia. I mentioned Higgs there, and this is where our electron and photon differ. Every particle that has mass interacts with the Higgs field. This interaction is what people talk about when they say the Higgs field gives things mass. But how? The Higgs field serves as a way of giving or maintaining the frame of reference for our particles. I like to imagine the Higgs field like a lazy oscillator. Let's pretend our massive fundamental particle is this standing wave. The Higgs field vibrates right along, sleeping on top of the wave function. Suddenly, the particle is accelerated and its wave function now has more energy. The Higgs field is jostled awake and goes, "No haga eso, chico."